A nuclear power plant looks like a standard thermal power station with one exception. The heat source in the nuclear power plant is a nuclear reactor. As is typical in all conventional thermal power stations, the heat is used to generate steam, which drives a steam turbine connected to a generator which produces electricity. Many reactors rely on proximity to the coast to draw seawater used to cool the condenser. And the plant shouldn't be located too far from end users, since much electricity is lost in long-distance transports. New reactors have not been built for many years. This increases the risks in terms of failing to meet time schedules and potentially increasing the cost. This uncertainty, though, is being gradually reduced as new plants are built. As you can see, the nuclear power plant consists of two main buildings. Containment building houses nuclear reactor. Turbine building houses turbo generator. The containment building is the key building of the nuclear island. It is an airtight building, which houses a nuclear reactor and its pressurizer, reactor coolant pumps, steam generators, and other equipment or piping that might otherwise release fission products to the atmosphere in the event of an accident. Such buildings are usually made of steel-reinforced concrete. The turbine building is the key building of the conventional island. The turbine building houses a turbine, generator, condenser and other equipment, which is used for conversion thermal energy from pressurized steam to mechanical work used for drive the generator. Also, a cooling tower can be part of the nuclear power plant, but it is not necessary. Many nuclear power plants do not cool the cooling water via cooling towers. Nuclear reactor, formerly known as an atomic pile, is a device used to initiate and control a sustained nuclear chain reaction. Nuclear reactors are used at nuclear power plants for electricity generation, and in propulsion of ships. Heat from nuclear fission is passed to a working fluid, water or gas, which runs through steam turbines. These either drive a ship's propellers, or turn electrical generators. Nuclear generated steam in principle can be used for industrial process heat, or for district heating. Some reactors are used to produce isotopes for medical and industrial use, or for production of weapons-grade plutonium. Some are run only for research. Nuclear reactors operate on the principle of nuclear fission, the process in which a heavy atomic nucleus splits into two smaller fragments. The nuclear fragments are in very excited states and emit neutrons, other subatomic particles, and photons. The emitted neutrons may then cause new fissions, which in turn yield more neutrons, and so forth. Such a continuous self-sustaining series of fissions constitutes a fission chain reaction. A large amount of energy is released in this process, and this energy is the basis of nuclear power systems. The reaction continues with the number of neutrons increasing, and the energy keeps increasing. Notice the binding energy of each uranium nuclide that is bombarded by a neutron. The energy is up to 200 megaelectron-volts. That energy is huge, and yet it keeps multiplying as the reaction went on. In a nuclear reactor, the chain reaction is maintained at a controlled, nearly constant level. Nuclear reactors are so designed that they cannot explode like atomic bombs. Slow neutrons strike nuclei of uranium-235, causing the nuclei to fission, or split, and release fast neutrons. The fast neutrons are absorbed or slowed by the nuclei of a graphite moderator, which allows just enough slow neutrons to continue the fission chain reaction at a constant rate. There are a large number of ways in which a nuclear reactor may be designed and constructed. Many types have been experimentally realized. Over the years, nuclear engineers have developed reactors with solid and liquid fuels, thick and no reflectors, forced cooling circuits and natural conduction or convection heat removal systems, and so on. Most reactors, however, have certain basic components. All reactors have a core, a central region that contains the fuel, fuel cladding, coolant, and moderator. The fission energy in a nuclear reactor is produced in the core. The reactor pressure vessel is the pressure vessel, containing the reactor core and other key reactor internals. Most of commercial power reactors are light water reactors, PWRs and BWRs, which are cooled and moderated by high-pressure liquid water. For example 16 megapascals in case of PWRs, and therefore the reactor vessel must withstand high pressures. It is a cylindrical vessel with a hemispherical bottom head, and a flanged and gasketed upper head. The bottom head is welded to the cylindrical shell while the top head is bolted to the cylindrical shell via the flanges. The top head is removable to allow for the refueling of the reactor during planned outages. Fuel consists of elements containing fissile material along with a diluent. Fuel elements come usually in the shape of thin rods of about 1 cm in diameter and contain fissionable nuclei, like uranium-235 or uranium-238. These rods vary in number according to the size of the reactor. This diluting agent may be fertile material, or simply material that has good mechanical and chemical properties, and does not readily absorb neutrons. All diluents act as a matrix in which the fissile material can stably reside through its operable life. In solid fuels, the diluted fissile material is enclosed in a cladding, a substance that isolates the fuel from the coolant and minimizes the likelihood that radioactive fission products will be released. Cladding is often referred to as a reactor's first fission product barrier. The light water reactor, LWR, which is the most widely used variety for commercial power generation in the world, employs a fuel consisting of pellets of sintered uranium dioxide, loaded into cladding tubes of zirconium alloy, or some other advanced cladding material. The tubes, called pins or rods, measure approximately 1 cm in diameter and roughly 3 to 4 meters in length. The tubes are bundled together into a fuel assembly, with the pins arranged in a square lattice. The uranium used in the fuel is 3 to 5% enriched. Since light water, used in LWRs as both the coolant and the moderator, tends to absorb more neutrons than other moderators do, such enrichment is crucial. Variety of substances, including light water, heavy water, air, carbon dioxide, helium, liquid sodium potassium alloy, and hydrocarbons, have been used as coolants. Such substances are, in general, good conductors of heat, and they serve to carry the thermal energy produced by fission from the fuel through the integral system, finally either venting the heat directly to the atmosphere or transporting it to the steam-generating equipment of the nuclear power plant. In many cases, the same substance functions as both coolant and moderator, as in the case of light and heavy water. The moderator slows the fast neutrons emitted during fission to energies at which they are more likely to induce fission. In doing so, the moderator helps initiate and sustain a fission chain reaction. A reflector is a region of unfueled material surrounding the core. Its function is to scatter neutrons that leak from the core, thereby returning some of them back into the core. This design feature allows for a smaller core size. In addition, reflectors smooth out the power density by utilizing neutrons that would otherwise leak out through fissioning within fuel material located near the core's outer region. In most types of power reactors, a reflector is less important. This is due to the reactor's large size, which reduces the proportion of neutrons that may leak from the core region. All reactors need unique elements for control. Typically, a reactor is equipped with 3 types of rods for different purposes. 1. Safety rods for starting up and shutting down the reactor. 2. Shim rods for compensating for changes in reactivity as fuel is depleted by fission and neutron capture. And 3. Regulating rods for adjusting the reactor's power rate. They are composed of chemical elements such as boron, silver, indium and cadmium that are capable of absorbing many neutrons without themselves fissioning. The most important function of the safety rods is to shut down the reactor, either when such a shutdown is scheduled or in case of a real or suspected emergency. These rods contain enough absorber to terminate a chain reaction under any conceivable condition. Regulating rods are deliberately designed to affect reactivity only by a small degree. It is assumed that at some time the rods might be totally withdrawn by mistake, and the idea is to keep the added reactivity in such cases well within sensible limits. A well-designed regulating rod will add so little reactivity when it is removed that the delayed neutrons will continue to control the rate of power increase. Shim rods are designed to compensate for the effects of burnup, that is, energy production. Reactivity changes resulting from burnup can be large, but they occur slowly over periods of days to years, as compared with the seconds to minutes range over which safety actions and routine regulation take place. Most of the world's existing reactors are power reactors, providing the heat needed to turn turbines that run electric power generators. There are also numerous research reactors, and some navies of the world have submarines or surface ships driven by propulsion reactors. There are several types of power reactors, but only one, the light water reactor, is widely used. Light water reactors are power reactors that are cooled and moderated with ordinary water. There are 2 basic types, the pressurized water reactor and the boiling water reactor. In the PWR, water at high pressure and temperature removes heat from the core and is transported to a steam generator. Working principles of nuclear reactor. For better understanding, let's see the simplified nuclear reactor. A nuclear power plant is a facility at which energy released by the fissioning of atoms is converted to electrical energy under strictly regulated operating conditions. Fission chain reaction takes place in fuel assembly. Fuel assemblies are placed in the reactor's core, reactor vessel connected in closed circuit of pressurized water. The water enters the reactor vessel at 270 degrees Celsius. The water acts as a heat exchanger and moderator. While the fission chain reaction, thermal energy is released, water is heated over 320 degrees Celsius. The heated water passing through the steam generator, and returns to the reactor vessel through the closed primary circuit. Within the steam generator, heat transferred to the bundle of U-shaped tubes. This heat is enough to generate the steam from the secondary water circuit passing through the steam generator. The steam passes through the turbine section. After passing through the steam turbine, steam is recondensed into liquid water and returns to the steam generator for another cycle. This is called secondary circuit. Tertiary circuit of water is from the cooling tower and it is passing through the condenser to make the steam into liquid. Then the water is returned to the cooling tower for another cycle. Generated steam enters into the turbine section and rotates the turbine attached with the generator, and produces the electricity. Before a reactor is started up, the neutron population is near zero. During reactor startup, operators remove control rods from the core in order to promote fissioning in the reactor core, effectively putting the reactor temporarily into a supercritical state. When the reactor approaches its nominal power level, the operators partially reinsert the control rods, balancing out the neutron population over time. At this point the reactor is maintained in a critical state, or what is known as steady-state operation. When a reactor is to be shut down, operators fully insert the control rods, inhibiting fission from occurring and forcing the reactor to go into a subcritical state. Nuclear waste disposal. Deep geological repository. Types of geological repository for nuclear waste are: mined repositories, very deep boreholes. This is example how is waste stored in repository. Later in video we will see 3D animation of complete process. In the early 1970s an abandoned salt mine in Lyons, Kansas, is become only long-term geologic repository for nuclear waste in the United States. Repository received its first waste shipment in 1999. Since then, more than 90,000 cubic meters have come to rest here from around the U.S. Today example is Swedish repository. Nuclear power companies in Sweden jointly established the Swedish Nuclear Fuel and Waste Management Company, SKB, in the 1970s. SKB's assignment is to manage and dispose of all radioactive waste from Swedish nuclear power plants. SKB is responsible for a system of facilities used to handle all waste from the Swedish nuclear power plants. These facilities include a central interim storage facility for spent nuclear fuel near Oskarshamn, and a final repository for short-lived radioactive waste in Forsmark. Transport is by sea, using the vessel MS Sigrid. Almost any material can act as a shield from gamma or X-rays if used in sufficient amounts. Different types of ionizing radiation interact in different ways with shielding material. The effectiveness of shielding is dependent on the stopping power of radiation particles, which varies with the type and energy of radiation and the shielding material used. Shielding reduces the intensity of radiation depending on the thickness. This is an exponential relationship with gradually diminishing effect as equal slices of shielding material are added. In this 3D animation we will see how radioactive waste is delivered and stored in repository. This is example of high-level radioactive waste, but it can be used for all types of radioactive waste. Radioactive waste is stored in dry cask cylinder made from steel. Casks are transported from above ground to the deep repository. Deep repository must be made with quality of the rock mass, especially its fracture, homogeneity and the strength of the overburden. Moreover, the subsequent alterations to these structures will be very diverse, depending on their purpose. Repository consist of various types of mine workings, pits, chimneys, inclined passageways, horizontal corridors, caverns, vertical shafts and small cross-section corridors. In caverns or vertical shafts, casks with radioactive waste will be placed and sealed with concrete or bitumen. Thank you for watching. Please subscribe, like, and leave comment.